Let's quickly review dimensional analysis and what we discussed in previous session. Dimensional analysis is a branch of mathematics that is used to organize all variables that are relevant to a flow phenomena, such as flow around a sphere, flow around a cylindrical shape, flow around wings of an airplane, flow of water around dams, so on and so forth, into sets of pi groups. All right, these pi groups or pi terms, they're also called dimensionless numbers or dimensionless terms as well. So I'm going to write dimensionless numbers. Perfect. Once we have these groups, we can use them to obtain maximum amount of information from minimum amount of experiments. Remember that I told you that if you want to understand drag force over a cylinder that is inserted into the flow, you need to do a lot of experiments, and you will generate a lot of graphs explaining those experiments, right? Using dimensional analysis, you will generate one graph, and specifically one curve that has two pi's, pi 1 and pi 2, and these pi's are dimensionless numbers. Remember that this pi 1 was some kind of relationship related to Reynolds number, and this pi 2 was some kind of relationship related to CD or drag coefficient, right? And then no matter how you change the diameter of the cylinder, how you change velocity, how you change viscosity, because all of these variables are included in Reynolds number and CD, drag coefficient, you will end up having only one curve. So all those points for different experiments will fall on this curve. So you generate one curve, one graph for all different possible experiments that you could do. And that's very attractive to engineers because it saves time and it saves money. Then we talked about Pi theorem. Pi theorem was a procedure that allowed us to find out those pi groups, right? And pi groups are the dimensionless numbers that we are looking for. The Pi theorem was originally named after Edgar Buckingham, and in 1914, because he made this theorem so popular, they used to call it the Buckingham Pi Theorem. The Buckingham Pi Theorem tells you that if a flow phenomena depends on n physical variables, for example, velocity, pressure, viscosity, and so on and so forth, and if among these variables there are m primary dimensions. What are primary dimensions? Mass, length, and time, right? And then through dimensional analysis, as you learned, the n variables can be arranged into n minus m independent dimensionless variables. So dimensionless variables or groupings. Now you know that these groupings are called pi terms. Perfect. And once you have the function relationship between these pi terms, then it can be investigated experimentally to create those graphs that I showed you before, like pi 1 and pi 2. And you have seen some of these graphs over the course of this semester as well. You didn't know that these are derived from dimensional analysis, but I'm going to tell you and show you some of these graphs that you have been using in this course. We engineers love dimensionless numbers and graphs associated with them. Why is that? Let me explain actually on this beautiful graph. So Reynolds number, dimensionless number on your x-axis, and CD, drag coefficient, on your y-axis. There are three lines over here. The blue line is related to smooth cylinder. So they did an experiment for a smooth cylinder, and they plotted the results, and they got that blue line for smooth cylinder. They did the experiment for rough cylinder, and after a point they saw that the line changes a little bit, and they did also the experiment for a smooth sphere, and that's the red line. Now, the beauty of this is that it doesn't matter how big or how small the cylinder is, it doesn't matter how big or small the velocity is, as long as you find a Reynolds number, let's say over here, that matches your case, and then you continue this until it intersects with the line that you are interested in, you will be able to find drag coefficient. And that's it. Very simple. They did only a couple of experiments to develop these curves, and they can use these curves for any combination of velocity, diameter, so on and so forth. Very interesting, right? Now, this should remind you of another graph that you have used lately, and that's Moody diagram, right? Moody diagram is also based on the theory of dimensional analysis. Do you remember the axis of Moody diagram still? Let's talk about that. So Moody diagram is something like this. X-axis was Reynolds. And Reynolds, you already know that it's a dimensionless number. Y-axis was F. And F is friction factor, which is a dimensionless number. Now, you still remember that Reynolds was developed for two different flow regimes. One regime was laminar, and the other one was turbulent. For laminar flow, you had a line representing the variation. Let me sketch a better line. You had a line telling you about the variations of Reynolds and F. And if you remember, the equation for this line was 64 divided by Reynolds number. Now, for turbulent regime, for a smooth pipe, for example, it was something like this. For smooth pipe. Now, so based on theory of dimensional analysis, they came up with dimensionless numbers that represent the problem, namely Reynolds number and friction factor. And they sketched these lines for laminar and turbulent flow. But then they ask another question. So what if relative roughness of our pipe changes? And then they added another dimensionless number to this graph. And what was that dimensionless number? It's pretty easy right now, you know, right? It was the second y-axis, and it was called K sub S over D, or relative roughness. And K sub S is the sand equivalent roughness, and D is the diameter. So the unit for both, the dimension for both of these is length over length, meaning that it's dimensionless. And they came up with different relative roughness, right? And different curves for different relative roughness over the range of different D's and different V's were developed. So this is the final form of Moody diagram that you see in your textbook, right? Perfect. So Moody diagram also was developed by dimensional analysis, having 3 pi's. One pi was Reynolds number, pi 2 was friction factor, and then pi 3 was relative roughness. Now, this is how engineers develop these diagrams that are so useful when you are designing something. All right, speaking of Moody diagram and pipe flow, let's take a look at an example that shows us how friction factor, friction losses are related to different variables. Let's take a look at problem statement. A pressure drop delta P provides a measure of the frictional losses of a fluid as it flows through a pipe. It's nothing new to you. I've already shown you that when we were talking about pipe flow or flow in conduits, that delta P, or pressure drop between sections 1 and 2, for example, let's say that this is section 1 and this is section 2, divided by gamma, is equal to your HL, or head loss, right? So as it says over here, delta P provides a measure of the frictional losses of the fluid as it flows through a pipe. Now, what we're going to find is determine how delta P is related to variables listed. So what we're going to find is how delta P is a function of the variables that are listed. So the variables are diameter, listed over there, length, fluid density, fluid viscosity, velocity, and relative roughness. In this example, relative roughness has been defined to us by epsilon divided by D, or you can write K sub S over D. So we want to find this relationship between delta P that represents frictional losses and all the other variables, right? Okay, so this should be very familiar to you. This is a dimensional analysis problem. Remember that the purpose of dimensional analysis is to find those pi terms, dimensional groups that can relate different terms to each other, right? Okay, so what I'm going to do is, first of all, find the number of variables, and the number of variables is defined by n. N number of variables would be 1, 2, 3, 4, 5, 6, and 7. So I have 7 variables that are important in this phenomenon. All right, and next what I would do is write down the dimensions of different variables. So I'm gonna here write down the dimensions really quick, starting from delta P or pressure. So pressure, and also just if you don't know the dimensions like myself, you can go to table F1 of your book, which is in front section of your book, and find the dimensions for these variables. Dimension for pressure would be m divided by L times t to the power 2. Next one would be diameter. Dimensions of diameter is simply L. Next would be length. Length of the pipe. Dimension for that would be L again, length. Density or rho. Dimensions of density would be mass divided by volume, right? So m divided by L to the power 3. Dimensions of dynamic viscosity, you can work it out based on Newton's viscosity law, or if you know it by heart, it would be mass divided by length times time, or t. And then finally velocity, it's easy one, it's length divided by time. Did I miss anything? Yes, relative roughness, or epsilon divided by d. What's the dimension of that? It doesn't have any dimension, right? It's dimensionless. Length divided by length, dimensionless. So just to make sure that I'm following my notations before, I'm going to put them into square brackets. This is how you notify that you're talking about dimensions. Put all of them into square brackets. So, and this is dimensionless. All right, so the next step is to find out how many pi terms we have. First of all, let's see if we can find how many primary dimensions are involved in this problem. Do we have, between all of these variables, do we have mass at least once? Yes, we do have mass at least once. So we do have mass. Do we have length at least once among all of these variables that I have listed here? Yes, we do have length at least one. Do we have time at least once? Yes, we do have time at least once. So m is 3. We have all 3 primary dimensions, mass, length, and time. Great. So how many pi terms do we have? Remember that in order to find the number of pi terms, the only thing that you need to do is number of pi terms would be equal to n minus m. So it would be 7 minus 3. You will have 4 pi terms, meaning that you will, at the end of this problem, when we are done solving this problem, we'll see that there are 4 dimensionless pi terms that we have. Perfect. Now, another step is to find or select the repeating variables. So we're going to select repeating variables. All right. Repeating variables are easy to find. We just need to find 3 of these variables that I have listed here. Those 3 collectively should have all MLT dimensions, right? So for example, I'm going to select d, v, or velocity, and rho. So let me mark them over here so they are more clear. So I'm going to select d, velocity, and rho. Why? Because among these 3 selected repeating variables, they have length, they have mass, and they have time. So these 3 variables are my selected repeating variables. Now, what would be our remaining variables? I'm going to write it using another color. The remaining variables are all but these 3 variables that I already selected. So it would be delta P, it would be L, mu, and epsilon over d. All right, this is how you select your selected and remaining variables. Now, when you are selecting your repeating variables, there is one point to note. You cannot select epsilon over d as your selected repeating variables. So you cannot select this over here. Why? Because it's already dimensionless. And remember, previous session when I was listing the rules, the procedure for you, I told you your repeating variable cannot be already dimensionless. Cannot be dimensionless. Perfect. So now that we have selected our repeating and remaining variables, we are going to continue next slide and see if we can find all those pi's. According to previous slide, we're going to have 4 pi terms. And we know our repeating and remaining variables, so it should be very easy to write the equation for different pi terms. Pi 1, for example, is going to be repeating variables to unknown powers, a, velocity to power b, and then rho to power c times delta p. Okay. Then the next step is to write down their dimensions. So it would be length to the power a, length divided by time to power b, mass divided by length to the power 3, everything to power c, and then dimensions of pressure is mass divided by length times time to the power 2. All right, let's write everything in terms of mass, length, and time. So it would be mass c plus 1 times length a plus b minus 3c, and then t negative b minus 2. And so you know that the power of m, l, and t should be equal to 0 because pi 1 is a dimensionless number. So writing the set of equation that I'm going to analyze, c plus 1 is equal to 0, a plus b minus 3c should be equal to 0, and minus b negative 2, or negative b minus 2 is 0, 2. When you solve this equation, you will have a equals 0, b equals negative 2, and c equals negative 1. And then put these numbers in pi 1 equation. It would be d to the power 0, velocity to the power negative 2, and density to the power negative 1 times delta p. Do some reorganization, and it would be delta p divided by rho v to the power 2. All right, so this is your first dimensionless number, or pi 1. Now, this process should be repeated for another pi as well. So what I'm going to do is to do a line here and repeat this process for pi 2. Again, you will have d velocity rho, this time times l, another remaining variable. And you can have a, b, c over here. One point that you might use is sometimes having multiple ABCs could be confusing. So some people, instead of having A, B, C over here, they're going to use other alphabet letters. So A, B, C, D, E, and F. It might be less confusing, depending on what you are going to do. So in my notes, I have, for example, H here. So I'm going to do powers of D, E, and H. The process is the same thing. You just need to write down different dimensions for these. Let's do it really quick. It would be, again, L to the power D to the power E and then write it down in terms of M, L, and T. I have done that before too. So it's M to the power H, L to the power D plus E minus 3H, T to the power negative E. And so again, you will form an equation based on this, a set of equations, which says H should be equal to 0 based on what you have. And then you have D plus E minus 3H equals 0. And also you have simply negative E equals to 0. Based on this, you have the values for D, which is negative 1, h is 0, and the other value would be e, which is 0, 2. So writing down the equation for pi 2 would be d to the power -1, velocity to the power 0, rho to the power 0 times L, right? All right, so if you reorganize this equation, you will have L over D. And that is, if you want to check if this pi 2 is a dimensionless number, length divided by diameter, because the dimensions for length is L, the dimensions for diameter is L, and they cancel each other out. So yes, your pi 2 is also a dimensionless number as well. You can do the same thing for pi 1 and check if it is dimensionless, and you will see that yes, it is dimensionless. So far, I have found pi 1 and pi 2. These are 2 of the 4 pi terms that I have written here. I'm going to do the same calculations for the other pi's in next slide. All right, we have 2 more pi's to work out. Pi 3, I'm going to write it quickly over here. It would be d to the power I, velocity to the power j, and density to the power k times dynamic viscosity. So I'm not going to go over writing all the dimensions for you. Let me just tell you that when you solve everything, you will end up having I equal to -1, j would be -1 as well, and k would also be -1. So you'll write the equation for pi 3, and you will see that it would be something like mu over d velocity times rho. Or just to write it in a more familiar way for you, it would be rho velocity d. Okay. Now notice that this term is very familiar for you, right? So this term would be Reynolds inversed, right? Because Reynolds inverse is 1 over Reynolds, and if you write down Reynolds number, it is rho Vd divided by mu. So Reynolds inverse is mu rho Vd. So because this term is basically represents Reynolds inversed, we are going to consider pi 3 inversed as well. And if one number is dimensionless, like Reynolds number, the inverse version of that number is also dimensionless, right? So this is also dimensionless, which is this one. All right, that was pi 3. Let's do quickly pi 4 as well. Pi 4, finally, which is the last pi that we are going to do, I'm going to do diameter to the power, let's say, L, velocity to the power m, density to the power n, times epsilon divided by d, which was our remaining parameter. Perfect. So solving this equation, I'm not going to go over all details, just going to tell you that L will end up to be 0, m would be 0, and interestingly, n is also 0 too. So when you write the equation for pi 4, it would be d to the power 0, v to the power 0, rho to the power 0 times epsilon divided by d. So all the zeros, these are basically all 1. So your pi 4 is, interestingly, epsilon over d. Now, what's the dimension of epsilon over d, which was your remaining variable over here? This is dimensionless, right? I'm just going to write dl, dimensionless. So obviously, in order for pi 4 to stay dimensionless, the power for diameter, velocity, or density should also be 0, right? Because you want to keep that pi dimensionless. So it totally makes sense that the power of those 3 are dimensionless. And that's our 4th pi. In the beginning, when we wanted to solve this problem, we could save some time for ourselves and realize that, well, because this is already dimensionless, I'm going to actually include it into the pi's from the beginning and tell you that, okay, one of the pi is already epsilon or k sub s over d, so I'm not going to include it into my calculations because I already know that this is dimensionless, right? Okay, so now that we have all the pi's, let's write them next to each other and see what we ended up having. All right, a quick recap. We started this problem having this equation. We wanted to find the relationship, the function, right, between delta P, pressure drop, and all the other variables that I listed, right? Now, what we did, we found the important dimensionless numbers, all these 4 different pi's, right? So right now, I can write an equation that relates these pi's together. So because I want to find delta P, which pi has delta P in it? This pi, pi 1. So I'm going to say that pi 1 could be a function of pi 2, pi 3, and pi 4. Now, if I write this down, it would be delta P over rho v to the power 2 is a function of L over D, pi 3, I'm going to use pi 3 to the power -1, Reynolds, and also pi 4 is K sub S or epsilon over D. All right, let's write it a little bit more organized. Delta P is going to be, I'm just going to put rho and velocity to the power 2 over here, a function of L over D, Reynolds, and epsilon over D. All right, so this, and remember that delta P represents kind of HL, like head loss. To be 100% correct, gamma times head loss, right? So head loss is a function of L over D, is a function of Reynolds number, is a function of epsilon over D. These are all your dimensionless numbers, and also times rho times V2 as well, right? Isn't this familiar to you? Remember this equation? This equation was Darcy-Weisbach equation, right? Now take a look at it. So you have L over D over here. This is your pi 2. You have HL over here, right? This is your basically pi 1, right? Some forms of pi 1 because delta P is this one, right? And then you have velocity term over here. This velocity term also represented over here. And F. And F was related to what? Remember, you find F using Moody diagram, right? And F was a function of Reynolds number and epsilon over D. So epsilon over D is over here and Reynolds number. So this is how Reynolds number was developed, and this is how they found out that whenever you have a pipe system problem, what to look for. And that's why that's the Darcy-Weisbach equation in combination with Moody diagram that you use to find head loss in a pipe. And remember that we wanted to find how delta P relates to other variables such as diameter and velocity. And for that purpose, we found 4 dimensionless numbers, and based on these dimensionless numbers, different researchers, different scientists did lots of experiments to find out the Moody diagram that you are using right now easily to find out different friction factors and Darcy-Weisbach equation as well. So the purpose of this example was to give you a clear idea of how these diagrams are developed, that we are using them with ease of mind to find exact values of friction factor to be able to calculate head loss in a pipe system. So far, you are familiar with a couple of dimensionless numbers or pi groups that I have introduced you. For example, Reynolds number or force coefficient, drag force coefficient, right? But let's dig deeper to the idea of having dimensionless numbers. Let's analyze one sample dimensionless number to see what it is composed of, right? And the easiest one would be Reynolds number. So I'm going to start with Reynolds number. Reynolds number for a pipe with diameter D, as you know, is velocity times diameter divided by kinematic viscosity, or you can write it in terms of dynamic viscosity, which would be rho times velocity diameter divided by mu, or dynamic viscosity, right? This is for a pipe with diameter D, but you might remember that the general form of Reynolds number was using a characteristic length. So if I want to write the general Reynolds number, not just for a pipe, it would be something like this. Velocity, L is a characteristic length. I don't care, it could be diameter, it could be length of something, divided by nu, or if I want to write it in terms of dynamic viscosity, it would be velocity, characteristic length, and dynamic viscosity. Okay, so I'm going to take the general form of Reynolds number and modify it a little bit. So let's take a look at it. The general form is rho velocity length divided by mu, right? I am going to multiply that by velocity over velocity, multiplied by length over length, and multiplied by 1 over length over length. Basically, I did nothing, right? Because they all cancel each other out, so I did nothing. However, this will allow me to write Reynolds number in this form. So it would be rho, and in the numerator, you have velocity to the power 2, characteristic length to the power 2. And in the denominator, you will have mu, velocity over length, and then length to the power 2. All right. Why did I write Reynolds number in this form? Because I'm going to conclude what would be the denominator and what would be numerator in terms of known formulas that I know. Let's start with a numerator. So let me change the color over here. So I'm going to start with numerator of this Reynolds number. All right, so numerator is dynamic pressure times area. So what was dynamic pressure? Remember that this term, velocity squared over 2g, was dynamic head, right? Dynamic head. So I can tell you that rho times velocity to the power 2 divided by 2, it's dynamic pressure. How did I get that? Well, head is in the units of length, right? In order to convert head to pressure, you need to multiply it by specific weight, gamma. So if you multiply this term by gamma, you will get this, which is dynamic pressure. Now, take a look at it here. This term, I'm going to change my color to change the color of the pen to green. This term, rho velocity to the power 2, is basically this term, right? So it's a kind of representative of dynamic pressure. So I'm going to say this dynamic pressure times, what's the next term over here? The next term is over here, L to the power 2. L is length. L to the power 2 would be some representative of area, right? Cool. Now let's take a look at this as a whole. Pressure is basically force divided by area, right? And so this term is force divided by area, and this term is area. So overall, this will give me some kind of force. What kind of force? Inertia force, right? Or kinetic force. I'm going to write inertia force. Or kinetic force. So now we know that numerator is some kind of force, inertia force, as a result of inertia or kinetic. Now, let's talk about denominator. Denominator, this part of it that I am going over right now, this should be very familiar for you. Remember tau? Tau was mu times dv over dy, right? All right, so this is your mu, this is velocity, mu and velocity, and then length, then length. All right, so the first term of denominator is a viscous stress or shear stress. So I'm going to write the first term is viscous stress, right? Times, what's the second term? The second term over here is, again, L to the power 2, some kind of area. Now, stress was force divided by area, right? Force divided by area times area would be some kind of force. What kind of force? It would be viscous force. All right, so based on this, I can tell you that Reynolds number, which is a dimensionless number, or which is a pi group, is ratio of inertia force over viscous force. All right, and that's why we use Reynolds number in pipe flow problems. Let me explain. Imagine that you have oil in your pipe. Well, you know that oil is way more viscous than air or water, right? So your viscous force over here is going to be high, and when the denominator of this fraction is high, Reynolds number should be smaller, right? So flow of oil in a pipe would be laminar. Makes sense, right? Now let's talk about air. You have air in your pipe system. Air is not viscous, right? Obviously. Air is not that viscous as oil, so viscous force would be smaller and Reynolds number would be higher, meaning that flow of air in a pipeline is what? Turbulent. Now you understand why you use Reynolds number to understand if the flow regime is laminar or turbulent, right? Perfect. So this is why we use Reynolds number in these kind of problems. Every single one of these pi groups or dimensionless numbers that I have listed over here, and basically this table is table 8.3 of your textbook, they can be used in specific use cases. For example, let me talk about some of them. Here we have a number called Mach number, which is velocity divided by velocity of sound, the standard velocity of sound. So as you can see over here, it is a fraction of kinetic force or inertial force divided by compressive force. So whenever you have high speed or high velocity, instead of using Reynolds number, you will use Mach number. Why? Because when the velocity of air is high, the flow can be considered compressible. Okay, and you use Mach number instead of Reynolds number. So you can imagine that when you are investigating the flow around an airplane, because the velocity is very, very high, you're using Mach number. Another one that is going to be very useful for us, and you will learn more about it in Engineering 467, Water Resources Engineering, is Froude number. Froude number, this number over here, is a fraction of inertial force or kinetic force divided by gravitational force. So the formula for that is velocity divided by square root of g times L, and L is a characteristic length again. This dimensionless number is used in open channel flow. The flow of water around bridge piers, the flow of water in channels, open channels, the flow of water over spillways of dams, you will use Froude number to investigate that number. So now that you are almost at the end of Engineering 368 fluid mechanics, you're learning that for any specific phenomena, flow phenomena, you need to use specific dimensionless number to make sure that you are considering forces that are related to that phenomena. For open channel flow, the forces that are related are inertial force or kinetic force and gravitational force, because it's gravity that basically carries water from one point to another point. For pipe flow, we use Reynolds number because viscosity is important and inertia is important. For flow around airplane, because we are dealing with high speed, we are using Mach number. And so on and so forth. We have lots of dimensionless numbers that can be used for different problems. This slide was just an introduction to some of these dimensionless numbers. We mainly use Reynolds number, force coefficient, and Froude number, and you will see how we are going to apply these numbers in similitude or study of similarity. Now it's time to introduce you to the last topic that is going to be discussed in Engineering 368 this semester, and that topic is similitude or similarity studies. Let's take a look at the photos that I have provided for you on this slide. The right-hand side photo is a model, and the left-hand side photo is prototype, or the real-life example of what you make a model of. So it's all right. Obviously, the model of this dam spillway, and this is Oroville Dam in California. The model was built in laboratory, right? And you can see that it's way smaller than the prototype, than the real deal. Obviously, in civil engineering, it would be very, very expensive to create a prototype size or the real life size of dams and try to test them to see what can go wrong and what went wrong, right? Because of that, you need to scale things down, right? By scaling things down, you will create models, and then you can study those models easier, obviously. And again, you will spend less money on creating those models. But how to create that model is art, and it requires a lot of engineering and math as well, right? So similitude or similarity studies is the theory and art of predicting prototype performance from model observations. So again, in the photos that I have provided, Oroville Dam had some incident in 2012. because of cavitation, and this is the spillway of Oroville Dam over here, because of cavitation, as you can see over here, parts of this spillway due to cavitation was destroyed because the flow was really, really big, and the dam was not designed, the spillway was not designed for that kind of flow because the velocity was very, very high, pressure was low, those bubbles were created, and the bubbles burst, and the spillway was damaged, right? Now, in order to study what happened in 2012, they created a model in laboratory like this. And they started to analyze what went wrong to be able to predict or to be able to estimate what went wrong in the prototype and the real-life example. Okay. Now, as you can see over here, that was just one example of the dam, Oroville Dam, but models are usually used to study the three-dimensional flow of water or flow of air, or whatever your fluid is, around an object having complicated geometry, like a spillway. If the model and its testing environment are properly proportioned, and that's a very key part over here, properly proportioned, the experiment will enable us, or the engineer, to predict how the flow will affect the prototype or the actual object for which the model is made. Now, the question is, how do we make sure that our model is properly proportioned? To make sure that our model is properly proportioned, we need to make sure that we are following three different types of similarities. The basic one is geometric similarity. What do I mean by that? So let's say that you want to create a model of a sphere that drops into water, right? Obviously, because the prototype is a spherical shape, you cannot go to the lab and use a cube, right? Because the shape is totally different. That's your geometric similarity. So if you are modeling a sphere, you need to use a sphere in the lab. You cannot use a pyramid. You cannot use a cube, obviously, right? So whatever, in other words, basically the length of different parts of your prototype should be somehow related, should be scaled to the length of different parts of the model, LM. And remember that you should remember that it's only about length. It's not about angles. Meaning that if this, for example, this angle over here is 30 degrees, in the lab, this should be 30 degrees as well, right? How about length? If this length is x, this length could be x divided by 10 or x divided by 20, depending on the scale that you want to use, right? So geometric similarity basically means that you need to scale down all the length. Now, the second criteria is kinematic similarity. What is kinematic similarity? So you know that kinematic refers to velocities. In other words, the velocities that you're using in your model should be proportioned to the velocities that occur in the prototype, right? So you cannot have one flow rate in your spillway in the dam and then go to the lab and increase the flow rate or decrease the flow rate to the level that you want to. They should be proportioned in prototype and the model. And eventually, the last part is dynamic similarity. And you know that dynamic refers to forces. If there are forces that apply to any point in your prototype, that force should be, the direction of that force should be parallel to the direction of force that is applied to the model. And the value of that should be proportional to the value of the force in your prototype. So once geometric similarity is satisfied, kinematic similarity is satisfied, and dynamic similarity is satisfied, your model is a proper model that you can use to study the real-life phenomena that can happen in your prototype. That's why there is a lot of studies before building a dam or before building a car or an airplane, because these are big things, right? You want to make sure that everything works on a model first and then move to the real deal.